let's talk about what Intel is now. It's XPU. It's not CPU. It's XPU. It's different architecture for computation. It's cross-architectural programming, one API, and heterogeneous memory. Intel obtained persistent memory. So let's talk one by one. Intel is not just somebody who manufactures semiconductors. This company has been creating the whole ecosystem for over 50 years, and I don't think it'll be an exaggeration if I say that the majority of instances of PostgreSQL runs on Intel platforms. And we are very active in semiconductor physics. Well, clearly that's our core competency, and we are developing architecture starting from processors, processor commands, processor designs, and down to data center architectures. And our biggest strong part is a huge global ecosystem of our users who work on Intel platforms, who optimize their projects to them, and we may say that the majority of those projects are open source developments, and we have a real big number of users who work together using our products to get their various tasks done. So let's talk about our present and about near future. Well, everyone knows XPU, but Intel wouldn't be called Intel if we were stopped and not expanded. So if we are talking about processors, it's a scalar computational approach, unit operands. But the next evolution, next to move towards vector, it was GPU. Well, modern CPUs can run vector transactions like in modern designs and in modern client ecosystems. So they use different things, but initially it was vector data arrays, and in case of CPU, this vector part was just added. Then as SoC we have as matrix, and there is a totally different space is FPGA, where it's not a program configuration. Well, how do I put it? Not a program, but configuring the matrix from load tables, from computational elements. And being a person who started with accelerators in my own time, and I spent a lot of time in the beginning of 2000s competing to Intel processors, I have the right to say that CPU, they are unique in something common. Yeah, they do not give you the maximum efficiency, but they are so universal and they are developing. So any accelerator that appears at a certain point of time in its narrow sphere of CPU application, it's in advance, it's ahead. And in next time and develop in the next loop of development, there is more development, 520 and so on. And CPU retains its universal applicability, and people in the database would really like it for that. But accelerators, they stay this narrow accelerators in the narrow sphere. They have their own niches that give good results, but niche is a niche, something narrow.
So right now, we talk a lot about database acceleration and database acceleration based on GPU. Last year, we presented a project on acceleration of Postgres FPGA, but from the point of view of mass use or consumption, CPU is number one that is used for databases, but also storage system. I could talk a lot also about storage, but it's a separate issue and very interesting one. As for database, CPU right now, this is the most important driving force, so to speak. As for Intel development, right now, apart from CPU, we also have GPU development. So I'm talking about discrete maps for servers. We have new brands that appeared not long ago, because previously we had a service CPU under Xeon brand, and the first Xeon was announced more than 20 years ago, and it was Pentium 2 Xeon that was issued in 1998, and actually it was representative of P6 architecture out of order superscalar that then became the basis for all core microprocessors. And now this brand Xeon is actually replenished by Z brand, and on the right hand side it is reflected as XE. This is a brand of a new GPU assortments of Intel, and moreover we also have a special ASICs which is Haban, and also it is available in Amazon Cloud and WC, and ASIC at Mavericks and IPG and Agilex specifically. But here this story continues an evolutionary way, and apart from developers, we also start a lot to work with heterogeneous memory, and accordingly Intel has always been one of the main producers for network elements. For example, 10 gigabytes ports, they are well presented based on Intel NICs interface cards. Last year we presented the first member of the Intel Xeon scalable family generation that is referred to as Quarter Lake. This is continuation of architecture Cascade Lake, but here we have twice as much UPIs before the connection between them, and this generation CPU Lake is actually aimed at multi-socket operation for databases, for sockets, and more. And moreover, this processor has another important function, which is support of default 16 for deep learning, and of course this format will be developed further on in the third generation, and then Copper Lake it appears for the first time ever. Here we can see some of the indicators. We can see quite a difference, which is quite considerable one, and we can see that it is very different compared to databases that date back to period like 5 years ago. That is why it's very important to keep a very close eye on those machines that you use in your work and compare them to Intel Xeon Scalable third generation. In the chat later on, I can provide you with more information about this new Xeon, and even more important to think about the fact that development of the Xeon and actually supports also Intel memory persistent. I mean, second generation. Here is the question. I just went through CPU, GPU, and ASICs for PG, and I also also announced a heterogeneous paradigm in computing. So how we're supposed to live all that and how it should be programmed. Postgres likes C, traditional C, where we actually have quite a big number of open source projects for a new closed platform, heterogeneous programming. We work on golden standards, and in order to make this golden standard C++ in a new world of different spheres of computing, and we decided to initiate and now develop it very actively one API. This is a set of standards and instruments, and it can be found along against these languages. With a big number of libraries that allows to actually perform the developments regardless of the executor actually that is used to work with the code. It can be a GPU, CPU, and FPGA, or something that has not even yet appeared in a product assortment of our producers. Here is the question. This is standards. This is not a proprietary thing. Like, for example, in the world of GPU. No, this is I would say something that is meant for the future. Right now, we are now working on that. We are developing an ecosystem, and in case you get interested in this direction, One API, I'm inviting you to website oneapa.com in order to get more information about it, and also subscribe to our emails. And you can also talk to Russian representatives of Intel. I think we could help you on that. So why? Because all those development works are registered, and they are have a main focus in Russia, here in Nizhny Novgorod region. A few words about data parallel C++. This is a standardized cross-architectural language. It is based on the expansions of ISO C++ and group Kronos SYCL. And the main extension is all about the fact that there natively we built in the special support of the mass parallel procedures. We have communities, engineers of Intel on that, and they want DPC++ to be as efficient as possible. And of course, we are joined by partners, and they say that they want to issue a compiler DPC++ also for GPU, that as well as for data parallel C++. You can use it to write codes on that, not only on those platforms where actually we have Intel engineers and who contributed to the development of this platform, but also other producers as well. You can go to oneapa.com. Here is a reference. You can see this is software.intel.com. This is Intel resource, and we provide this product and also provide access for everyone, and everyone can give it a try. I mean, this toolkit online. Apart from heterogeneous computing, well, we should say that memory also becomes heterogeneous. Why is it happening? Because, well, we should say that this is quite a general slide, but it actually reflects some dynamics of DRAM evolution. DRAM evolution, the first framework was developed by Intel, and it happened quite a long time ago, and ever since that time the density growth of DRAM technologies has been quite linear, and on top of that it's also slowing down a little bit. At the same time, demand on memory computing is growing right now, and memory in this configuration is expanded in size. And on by year 2023, the overwhelming number of machines will be equipped with over 520 gigabytes of memory. And on one hand, Intel is one of the pioneers in not SSD. The first one was issued in 2008, but as for NAT, as a flash technology, has quite strong inbuilt constraints, such as, for example, block writing of all the erased components, and it started to use it as an element absolutely autonomous from energy. We have different blocks here, and now it can be processed very easily. But if we cut down on the granular side, then we inevitably risk to have quite a few problems with that. And in order to move forward, and in order to switch from solid accumulators to a new one, capacitors, to a new device, we decided to create a new line into obtain based on 3D cross-point technologies. This is memory, and it is based on new physics. That is, on one hand, is absolutely free from dependent from energy. At the same time, it is byte per byte addressed, and so data is written immediately without any buffering, without any complicated manipulations. And SSD controller, which is simplifies all the works related to this stuff. You don't have to work with different blocks, and you don't have to perform cleanup of those blocks. SSD NAND technologies. And this, of course, speeds up all the processes related to obtain systems, and we don't have any considerable delays. And you have a feeling that if there was none, they are not dependent on any loads. And as for delays, it's data not fluctuates based on the common requests, as you can see with SDD. So actually the whole situation left on a situation where we first manufactured these blocks based on SSD, and in 2019 in April we presented obtain a persistent memory from factory DDR for demand. And so the first one, obtained a persistent memory 100 series, can be used with modern platforms. This is the first and second generation of Intel Xeon. It has 128, 256 and 512 gigabytes, while TDP is 18 watts. And at the same time, persistent memory can be used in two modes. It can be used in linear modes in order to boost memory, and in this particular case I'm talking about persistent memory, and it is then addressed to CPU, and depending on the application, and it doesn't matter where you actually store your data, whether it PIM or DRAM, and in this case DRAM is used as a memory buffer cache of fourth level. But even more interesting to talk about the situation where PMM is used in updirect mode, and here for the application we have to know that it has PMM, and you have to know how to work with that. We actually produce a new software low level where persistent memory development kit test for with libraries or PM opt that allows to simplify implementation and new releases of software PMM support. But at the same time, we also provide full-fledged support for the producers of for software for our platform. Thus, for example, I'm talking about the fact that we provide access to Intel DF clouds, and also machines with PMAM for testing for different development and research works for various projects. And like I previously said, in our Copper Lake third generation, we have support for PM200 series. So this is a second generation that was speeded up by 1/4, pretty much the same capacity, but TDP was decreased to 15 watts. And visually, you can see that 100 series is a bit different from 200 series in terms of the radiator color. Here it is dark blue, and the upper one is light blue. If PMAM is black, then it means 4 Xeons of second generation. I'm talking about parallel platform, and I should say that here PMAM 100 series, it was issued and produced with Cascade Lake, and it can only work with a second generation. That is what we actually have in terms of association. So Xeon second generation works with PMAM 100 series. Xeon third generation works PMAM 200 series. The first question that we have when we see it, why do we have new approaches or components in architectures that are already quite successful, the new elements of for example, here we can see persistent memory as SSD. They cover this gap between DRAM and block-based capacity storage. Previously it was HDD. Right now we are also promoting NAND SSD, QL NAND SSD. Here we work with big volumes and quite low thing in terms of gigabytes. But here we can see the rule of locality 90/10, and where we can see 10% of codes and memories. We have 90% of requests going on this 10%. So in order to have this continuous stepping in terms of volumes and productivity, in order to preserve it and to cover this gap between DRAM and HDD and SSD, we had to insert a number of additional levels in order to actually cover this 100 gigabytes and something that is less than 1 microsecond, and further on, as for terabytes, volumes and latencies, we have less than 10 microseconds delay, this kind of latency. Yes, that was done for that. And then we have some additional latencies, just less than 10 milliseconds for big traditional technologies like ferromagnetics or, for example, old SSD. So what future holds for us? Like I said, yes, persistent memory is being developed very quickly. So Barlow passed the official name for 200 series, and at the end of 2020 we got a new Intel Optane series 5000 Alderstein. This is the official name of this product. As for non-SSD, we presented actually, and also based on that we did it with a 400 series, and also here we can say 5500, 5600, and some other models 5300, and further on we think that this story will be developing together with other generation Intel Xeon software rapids and third generation's persistent memory. Here we have quite good solid roadmap, and in case you haven't yet started working with Xeon or second and first generation persistent memory, then you should definitely think about Xeon Copper Lake third generation and parallel pass. As for actually all these questions with whys and what success we have already achieved in terms of a persistent memory, especially when it comes to Postgres, well, I think I should give the floor to some Narыsh Kumar, CEO of a MemHive company that actually implemented PMEM in Postgres and also sped up it by 10 or even 15 times in some cases. Narыsh, please, over to you.
The reason I'm here presenting today with Mihai is also because of MemHive's partnership with Intel. Mihai just introduced us to Optane PMEM, and he showed us the memory storage hierarchy and the pyramid. Suffice to say that it is the best PMEM solution in the market today, both from a price and capacity perspective to vertically scale Postgres. Thanks to Intel, we have been able to perform our benchmarks on Intel's cloud servers with PMEM and scalable processors. Next slide, please. How does MemHive accelerate Postgres with PMEM? Well, it does that by providing full integration of PMEM in Postgres in terms of utilizing PMEM as both a memory and a storage device. It provides a PMEM resident persistent cache. It provides support for write-ahead log files on PMEM. It has an option of hosting the entire database's relation files on PMEM, and also provides an easy-to-use MemHive manager to orchestrate, install, manage, and monitor PMEM for Postgres. Mihai spoke about AppDirect FS-DAX mode in his slides. MemHive provides support for AppDirect FS-DAX mode in Postgres using the libpmem libraries provided by Intel's PMDK. Next slide, please. Next, thank you. Here's a quick look at the persistent cache feature, which is nothing but a PMEM-based non-volatile shared buffer cache. This is done by intelligently splitting the data structures of the cache between DRAM and PMEM. The buffer blocks and buffer descriptors are mapped to an FS-DAX PMEM namespace, whereas the shared buffer hash table resides in DRAM. CPU cache flushes and barriers are batched together at critical points in the buffer cache code paths to ensure durability. Not only that, these operations are performed only for selected buffer descriptor fields. The code uses a combination of PMEM memcopy no drain and PMEM flush plus drain as applicable. There are also a couple of additional things required to be done to ensure persistence of the cache. First up, the server restart paths are now intelligent to ensure that valid cache buffers are persisted and the remaining buffers are moved to the free list. We also have an optimization to avoid flushes, drains for certain operations like bulk copy and vacuum, where we trade off persisting buffers for faster completion times. Next slide, please. We have a couple of operating modes. A performance mode where both the shared buffer cache and the write-ahead log are on an FS-DAX PMEM namespace. This mode does not provide protection against local PMEM failures and can use a backup technique like Postgres replication. Whereas the second mode is the one which provides protection against local PMEM device failures by mirroring the relational files across PMEM sector mode devices. Next slide, please. Let's now look at a few interesting benchmarks where we truly see Postgres scaling well with PMEM. The tests compare a standard Postgres v12 instance against MemHive. And when I say the standard Postgres instance, it is a standard, it's a Postgres instance which was on a dual socket Intel server with 96 Cascade Lake Xeon processors and 192 gigabytes of DRAM, coupled with 800 gigabytes of SSD for relation data and write-ahead log storage. Memhive Postgres was run on the same server with 750 gigabytes of PMEM. Out of these 750 gigabytes, 400 gigabytes of persistent cache and 32 gigabytes of write-ahead log was used for the test. The graph on your screen is of TPCH OLAP benchmark showing something called the query processing power, or QPP, from a tool called DBT3. TPC, as you know, is a standard transaction processing benchmarking council. And the QPP number is obtained from a formula provided by TPC. QPP basically represents the ability of the server to run a sequence of single stream queries. The horizontal axis represents increasing database sizes. As can be seen, when the sizes of the database outgrow what can fit into DRAM, standard Postgres fails to keep up due to the heavy disk I/O, whereas Memhive manages to maintain a steady QPP due to the PMEM resident persistent cache, and eventually outperforms standard Postgres by about 5x at 230 gigabytes. And as you can see, when the size of the database fits into DRAM, standard Postgres performs better than Memhive. Next slide, please. The next graph is a TPCB like OLTP, a transactional benchmark from the popular tool PGBench for a test of select-only queries. Again, and of course, here we vary the number of clients. As you can see, Memhive with the PMEM-based persistent cache scales up to nearly 15 times the performance of a standard Postgres at 40 clients. Next slide, please. This graph is a read-write TPCB-like benchmark, again provided by PGBench. It performs inserts, updates, and selects, as you all know. And with the combination of the fast write-ahead log and the PMEM-based persistent cache, we can see how Memhive performs at 3.5 times the standard Postgres at 40 clients. Next slide, please. Lastly, we have an interesting graph here to actually show how Memhive Postgres with Intel Optane PMEM can dramatically reduce the DRAM requirements, which can be seen as one of the goals of a server that uses persistent memory, and it is one of the big wins of using PMEM. Here in this test, we have reduced the system's DRAM to 32 gigabytes. But as you can see, Memhive is still able to maintain, close to about 500,000 transactions per second in the select-only test, and also maintain a similar performance in the read-write test. Again, thanks to the PMEM-based persistent cache and the write-ahead log. Next slide, please. Yeah, that concludes my presentation about how Memhive scales Postgres with PMEM. For more information on Memhive and a white paper, do visit our website, www.memhive.io. Thanks for listening, and over to Mikhail.
Thank you. Yeah. Thank you, Narыш. Thank you, Narыsh. So just now we are open a Q&A session and invite all of you to join us in a chat with Intel and Memhive. Me and Narыsh will be available after their presentation for the special chat and text chat here. So also in chat my colleague Vasily Lizunov, who is a deep hardware specialist, and we will be glad to answer any question you want to ask Intel. So now Q&A. Do you have any question right now? Any questions from chat?
Могу. Yeah, so we have already some questions in chat for you. So the first one is, do we need a battery for PMM?
No, it's a very important thing. So just what the different from the first generation of NVDIMMs? Yeah, the first generation of NVDIMMs, not Intel, were done by a battery or supercapacitor, but the media was really energy dependent. But for PMM, Intel PMM, we use the true power independent technology. It's something like NAND flash, but based on different physical principle. We don't need any power batteries, supercapacitors for PMM. It's a truly persistent memory.
Okay, thank you. Okay, so the next question is, how many rewrite cycles does PMM can handle, and how do you diagnose PMM that PMM cannot be used, and which technologies? Okay, so let's go with the first question. So how many rewrite cycles does PMM has?
Absolutely valid question. So persistent memory wherein cycles are in magnitudes higher than traditional NAND storage. Frankly speaking, even DRAM has wearing out cycles, which are relatively high if you're comparing to SSD, but persistent memory has a lot of DVD-PD cycles, data writes per date, and in general it's a number in hundreds of DVD-PD for PMM, and of course PMM has own variant out monitoring mechanism. So PMM module, each PMM module has its own tiny controller which counts writes and checks potential failures and variant for specific addresses. But I can say this task is also relevant for now for traditional DRAM modules. DRAM modules with big sizes and with huge numbers into modern server also has big issues with reliability. And Intel works in that direction, providing a new technology named Memory Failure Predictor Analysis MFP tool for DRAM only. But in case of PMM, we have a big advantage. The incorporated controller in each PMM module, which is responsible for wearing out cycles and the failure prediction in that module. So PMM in that case even more reliable than DRAM without such controllers.
Okay, thank you. So you answered the next question in your answer, because the next question was about how to diagnose worn out PMM. And okay, so the next question is, what is the size of shared buffers for standard Postgres in the TPC-H, TPC-B benchmarks?
I think it's a question to Narыsh.
Yeah, so the shared buffer cache in the standard Postgres was set to 64 gigabytes. Actually, the tests were run with the NUMA-aware application. So although the system had 192 gigabytes of RAM, about 90 gigabytes of file system cache was used. So I would say the actual database was using about 90 gigabytes of file system cache. 64 gigabytes, of course, was the shared buffer size.
Okay, thank you. So, and the next question, it is true that memhive shows better results only because database doesn't fit in DRAM shared buffers?
I would say so. You mean in the with the standard Postgres, if you're able to fit the database into DRAM, then like the graph showed, you would get superlative numbers even with standard Postgres. But yes, the difference starts showing up when the sizes of the databases start outgrowing the size of RAM, and it has to do disk I/O, and that's where PMEM comes in a big way.
Okay, thank you. And the next question is, what does really 3D X-point technology and on-obtain is? Is it a phase change memory or something else?
Yeah, it's a big technology secret. So it's a good question, and this question is raised many times, but at this moment we don't disclose the specific physical principle behind 3D crosspoint.
Okay, so I guess this also answer question like, is memhive is some Postgres, another Postgres distro? Yeah, I guess it answered that question also.
Yes, it does. Yeah.
Yeah. Okay. So, I guess that sums it up. The questions. Yeah. Okay. So sorry. It's like another question is. Just a minute. Does Postgres Pro plans to do something like this? I don't think that
yeah, I
you
think
can.
It's better to address this question to our colleagues in Postgres Pro.
Yeah.